So hello everyone. So my name is Quentin Boehler. I'm from the Multiscale Robotics Lab, ETH Zurich, led by Brad Nelson. So today, presentation is about a new simulation framework for soft magnetic tools in medical applications. So first, I would like to thank the collaborators I have on this work. So Roland Dreyfus, who is a PhD student in the lab, who helped a lot on what I'm going to show you today. Hugo for introducing to us to SOFA in the first place, Christian, of course, for the initial push for the use of SOFA and the Bim Adapter plugin. So what we're doing is using soft magnetic tools. Whoops. So soft magnetic tool is essentially a flexible beam along which you have one or several magnets that are arranged, and it is essentially remotely actuated via an externally generated magnetic field which is going to interact with the magnets and apply torques and forces along the tool to control its shape. So these tools, as you can see here, are, that can be extremely small and soft, and they exhibit a very high dexterity. So this type of motion you can see on the video here is unusual for this type of tool. So it got great potential for medical applications, obviously. So our group has more than 15 years of experience with this technology. The most noticeable one is back in 2010. We have this spin-off company from us called Ion Scientific, which developed a clinical magnetic navigation system, which is essentially a machine who is used to generate these magnetic fields to steer magnetic catheters, in that case to treat cardiac arrhythmias. So this demonstrated at the time that the technology could be used for clinically relevant tasks and ultimately propose a viable alternative to standard manual tools with increased safety thanks to the actuation method. And so we are currently working toward more efficient and smaller magnetic navigation systems and also trying to target other medical applications. We also want to bring automatic features to control the tools, obviously. One of the key components for the automation, obviously, is our ability to model and simulate these tools in real time. A few years ago, we based our first implementation on constant curvature and cost rod models, and we notably investigated the stability of these tools, which actually are subject to very interesting singular behavior, such as the one illustrated here on the right-hand side. As you can see here, the tool is basically just snapping from one configuration to the other when submitted to the rotating field. Anyway, what you can see here is the implementation of our original rod model, which you can see the magnetic field here represented in red by the red arrows, and this is essentially here one catheter with one distal magnet at the tip. And so this approach suffers from several limitations. Well, as you can see here, you have a fixed length. The main problem is that you cannot consider obstacles. So this is valid only in upper space. We do not model any interactions on the catheter. And it's only for beam-like structures, obviously. So looking toward using these tools for medical applications, there are two main challenges we want to overcome: be able to interact with complex anatomical environment, and do real-time simulation for surgical training. Now, SOFA actually provides the perfect platform to tackle these challenges, more specifically making use of Bim Adapter, which is a plugin to model beam-like structures. You can see an implementation here on the video. So the field is represented by the green arrow, and you can see the beam getting in interaction with the region environment. And so overall, we had to implement two new features to use SOFA in our case. We had to integrate the torques and forces on the tool due to the externally generated magnetic field. And we had to implement a feature to couple SOFA to our existing software platform that is based on ROS. You can see some further implementation here on SOFA and a picture of, well, visualization that we did using ROS as well, with always the magnetic field depicted with the red arrows. So the very first thing we did to check our implementation is to simulate the behavior of a tool in 2D in a non-rigid geometry for obstacles, so just rigid pins that you can see here on the pictures. And the input of the simulation was essentially just the magnetic field and the inserted length. And what we wanted to show is, well, pretty much what you see on the video is that, well, we wanted to show that we can match what happens in reality well with SOFA, and that works actually pretty well. We also tested with more complex tools and in more complex environments, and it still works pretty well to predict the shape of the tool. Now, looking toward the medical applications, one of the applications we're focusing on right now is, and that's what we think going to benefit from this framework, is endovascular navigation. Essentially consists in steering a tool magnetically under fluoroscope guidance to reach brain vessels and treat brain aneurysm, for example. So we developed magnetic navigation system, dedicated tools together with a user interface and dedicated controller. And the use of the simulation in that case is twofold. First, we develop training exercises for the surgeons to learn how to manipulate the field and to use it, and also using evaluation metrics. So in that case, what you can see on the video is basically controlling the catheter with this controller to reach dots in a given amount of time. And the second use is to do more realistic surgical simulators. So you can see here simulation of the aortic arch, which is kind of the entry point to the brain vessels. And you can see on the left-hand side compared to what the neurosurgeon is actually doing on the real system in vitro and the clinical models matches again quite well what we're simulating here. An interesting perspective for this simulation framework is also to try to generalize its use for more complex structures. And so the example I show you here is called magnetic ciliary carpet. The black part is a mix of ecoflax, which is a soft polymer, and magnetic particles. And what happens here is that by magnetizing the hairs on the carpet in a specific way, you can generate this mechanical wave that is traveling here along the carpet. And that can be used for fluid transport, for example. And we can observe when it's submitted to a rotating field, we can observe the similar instability behavior. So the hair is going to snap the other way around in a similar fashion as what you've seen at the beginning of the presentation. The funny part is that it kind of depends on the magnetization of the hair. And anyway, what we wanted to show is basically that by using SOFA, we could kind of replicate the way these hair are snapping from one way to the other. And that, again, that worked quite well. And so the exciting part is that there is actually a lot of other magnetic structures, more complex one we could consider, you could try to model with SOFA as well. So opens a lot of nice opportunities there. We could consider the one that you see on the left-hand side here are essentially rigid magnets that are linked by soft links. And when you actuate them, it's kind of making these oxalic structures. You can see also the same device that I showed you before. If you essentially just put it upside down, you can use the mechanical wave to make a locomotion device, which is kind of looks like a millipede. Could be very interesting to try to model with SOFA as well. Now, the main bottleneck to consider more complex materials and geometries at the moment is that we don't have a specific SOFA plugin for magnetics. We're just using Python controllers. So the creation of this plugin would be hopefully the best way to go forward on that. And I also take this presentation as an opportunity to welcome anybody who is interested in working on these aspects or collaborating with us. We're always open to collaboration. We'll be glad to discuss the opportunity either online during the symposium or offline at a later date to talk about it. So that's it for my part. Thanks again for the attention, and special thanks to the organizers again and the collaborators.
Thank you very much for the presentation. It's super interesting. I think so I have already some questions. There could be many additional ones. So do not hesitate, as usual. Yeah, Eric is saying very interesting work. Thank you. So definitely for coupling, bringing SOFA with soft robotics was a first step done. I would say, 2-3 years ago by Defrost, and they're bringing electromagnetic fields into the simulation could have an unlimited amount of application. I think the one in medicine is the first one we think usually in the community, but it sounds really interesting. From what I got is that with an Xbox controller, basically we can just now practice radio frequency ablation from our living room. So that's
exactly
convenient.
It's PS4, it's not Xbox.
Okay, sorry. Yeah, it's currently a big fight. So yeah, and what I can also share with you all is that I don't know if you could see all the video. I don't know if there is a YouTube link already for all the videos that you shared, or if there is some places we can actually have some link to those videos. Otherwise, we can maybe directly ask you, Quentin.
Sure. Yep.
Yeah.
Was there a problem with the videos, or?
No, I mean, so it was not always super smooth, at least on my side. I don't know for others. What I can tell you, because it was not necessarily always striking, it's the fact that really the comparison that Quentin did between between the simulation made with SOFA for controlling the catheter with the Python script and the experiment was really bluffing as a first step.
That matched very well, yeah.
So yeah, it's a very interesting first step. There will be, I guess, many further next step. Hopefully, as you said, a plugin for electromagnetic fields for the next contribution award, definitely. And yeah, again, if you're looking for position, curious about that or whatever, that's something that I think we're going to look for people working on this topic. So do not hesitate to. I will not say apply directly, but there could be possibility definitely to work between ETH, INRIA, that's all around SOFA, so that would be nice. So a question from Eric: when you are simulating the magnetic field, do you discretize your 3D space, or is it only controlling the direction? So I think, yeah.
So you have very different ways of doing that, but essentially what we do right now is that we control the 3D field in one position. I mean, this is a degree of freedom problem, but essentially, let's say you have 3 electromagnetic coils, so you can control 3 currents. And so what you do is that usually it means that you can control the components of the 3D magnetic field in one position. And so all of the other arrows you see all around the space are just, these are what they are because you generate a set of currents. But usually what you do is you control the 3 components of the magnetic field at one position. If you add more coils, you can also control the gradient, so the way the field is changing along space. You have a very different way of doing that, but think about it as a robot where the inputs are the currents in electromagnets. Yeah, that's the way to see it.
Perfect. I got it, and that's actually all the project is also to have this 3D discretized, integrated in space electromagnetic force, which would be applied on here a catheter, but it could be actually on any kind of structure.
Well, it's a vector field essentially, yeah.
Mm-hmm. Mm-hmm. Any other question? Go ahead, Stefan.
I have a small question. What was I going to say? I'm sorry. Okay, I'll come back at you if I remember. Sorry.
Yeah, sure. No problem.
Anyone else while Stefan is recovering the memory? we all have sometimes some memory loss. So. Yeah, go ahead, Younes.
How do you plan to integrate it to the inverse path? I understand where you only have the direct path, right?
Yes, exactly. So, that was what we were talking about, right? What we can do right now is use the Python controller and our ROS implementation to determine which magnetic field is acting at the position of the magnets and compute the force and torques that are applied at the magnet position depending on the configuration of the tool. And so that's what we're going to have to look into if you want to use the inverse model. Can we still use this Python controller, or do we really need like a new plugin in SOFA for that? So I mean, I don't have really good idea for that right now. That's the part of the discussion we have to have.
Mm. I think it might depend on the complexity of the field applied and the model that you are actually controlling, which is magnetized. This will depend on that, but
that can be very simple actually. So that's the good news.